so far we've talked about everything we need to know about bell curves. We've talked about how if we have a data point, we can find the probability of being less than, greater than that data point. We can find the probability between any two values in a data point. And we've done that by equating probability with finding areas. And we've been using the bell curve table to be able to find any area. So that's a very powerful thing that we're able to do, but it only applies specifically to bell curves. If we have a distribution that is no longer a bell curve, we can't use the bell curve table. So now we have this very nice framework to be able to find probabilities for any bell curve. So moving forward, we're going to try to look at situations that aren't initially bell curves and try to massage them into situations where we can apply these bell curve techniques onto those problems that aren't originally bell curves. So this will be classified under situations in which we use bell curves in the class. So there's going to be three situations total. The first one we just talked about. And the first situation is the most straightforward. And it's that you're given that the variable in question is distributed as a bell curve. So in the previous example, we were given or told that weights are distributed in a bell curve. So this is the most straightforward situation. So distributed as a bell curve, another way to say that is normally distributed. Because a normal distribution is a bell curve. So an example question again might be, given that weights are normally distributed, with a given mean and standard deviation, so let's say with mean of 180, and standard deviation uh, 20 pounds. What is the probability that a random man selected has a weight less than 215 pounds? Then in this case, you're told that this variable, or a man's weight, is normally distributed. So this is given to you, and you're given the mean and standard deviation, and you're simply asked to find a left or right area to this bell curve. So this is what we've seen before. So now let's go over the second situation that is new, and I want you guys heads up. So these last two situations for which we use bell curves are, objectively speaking, the most difficult in the entire semester, the most confusing in the entire semester. So again, pay extra attention, ask extra questions. So this next time that we use bell curves has to do with a concept that we call the central limit theorem. So I'm going to build up to this slowly and carefully, and we're going to start with a motivating example. And we said that there are some variables in real life that were distributed as bell curves, like heights, like weights, like standardized test scores. But on the flip side, there's a lot of variables in real life that are not distributed as bell curves. So let's look at an example. Let's say that we look at cholesterol level. So I'm going to specifically call this individual cholesterol level. That means that if you take a random individual and measure their cholesterol level, and do that for lots of individuals, let's say you plot their cholesterol level. And so let's say that the distribution looks something like this. This is not a bell curve. So I'm going to kind of make up numbers here because cholesterol is measured in different ways, and there's also different kinds of cholesterol like HDL and LDL and so forth. But let's say that I only look at one particular kind of cholesterol. And let's say that I look at the mean here, and let's say it turns out to be 190. Let's say that's the mean cholesterol level of 190. And let's say the standard deviation turns out to be 10. But the main thing is that this distribution of cholesterol level is not distributed as a bell curve. So who can give us some intuition as to why that might be? So why do you have this distribution that's not a bell curve, and in particular has these two peaks? So what this means is that at some low cholesterol level, there's going to be a lot of people in the population that have that low cholesterol level. And at a high cholesterol level, there's going to be a lot of people who have that.
So it's not symmetric?
What is it?
It's not symmetric?
Yeah, it's not symmetric, but who can explain that in terms of why cholesterol in particular maybe is not symmetric and it looks like this? Yeah, maybe. But one explanation might be that cholesterol is something that is largely influenced by lifestyle and diet and exercise and so forth. So people could choose to live healthy lifestyles, or they could choose to not. And in that sense, they would align to either having low cholesterol or high. Okay, so this is just an example of a variable that is not distributed as a bell curve. So let's say that you take this population of people, and then let's say that you take a random sample, so let's say 100 people. So this will be a random 100. And let's say that you measure those 100 people's cholesterol levels. But let's say that you do the same thing. You plot a histogram of those 100 people's cholesterol levels. And for each particular cholesterol level, you plot how many people of those 100 have that. So what do you think the shape of that distribution will end up looking like? yeah, it should look like this one, but this one was plotted using the entire population, or all 300 million people, let's say. But this one's are only plotted using 100 people, but roughly the shape should be similar. So let's say it's similar, it looks like that. And let's say that what you do is you continue to perform this experiment where you gather a random 100 people. So this is another random 100. And then you plot that distribution, and it turns out to be similar, if not the same. And so on. So let's say that you repeat this experiment of gathering random samples of 100 people. And let's say you repeat this a number of times that approaches infinity, let's say 1 billion times. And let's say that each time that you have a random sample of 100 and you gathered 100 people and you measure those people's cholesterol levels, let's say that then you punch the 100 cholesterol numbers in your calculator, and the calculator will give you a mean. So let's say that you find the sample mean. So let's say you find the sample mean of each of these random samples of size 100. So you're repeating this experiment 1 billion times, where you're gathering samples of 100 each time, and each time you're finding the average value of that sample of 100. So at the end of this, how many sample means should we have? Yeah, we should have the billion of the number of times we're repeating this experiment. So at the end, we're going to have 1 billion sample means. So then, let's say that we then plot the distribution of the sample means. What do you think the shape of that distribution will look like? Will it look like these, the originals?
It should look like a bell curve.
Yeah, why is that?
Because the means will trend towards 190 and distribute down evenly across either side.
Okay, excellent. So when you plot the distribution of sample means, we're going to end up getting a bell curve. And the reason for that is because the mean of the individual cholesterol levels was each 190. So each time you take a random sample of 100, the mean is going to be roughly 190. It's going to be very close to this original population mean of 190. So each of these individual samples of size 100, the means will be close to 190. So let's say that this mean is 189, and this mean is 191, and so forth. The remaining means will be very close to 190. You're not going to have all this individual fluctuation that you had in the original distribution of individual cholesterol levels. So all these numbers will be very close to 190. So these numbers will be clustered closely to the 190, and all the other values representing the sample means will level off around the 190. So you're going to get this distribution that actually ends up looking like a bell curve. So this is a very important idea that we call the central limit theorem. So I'm going to write out what this says. So the central limit theorem says that no matter what the original distribution of individual values looks like, the distribution of sample means so all those x bars that we have, those are sample means. So the distribution of sample means will be normally distributed So all that's saying is that no matter what the original distribution looks like, it could be a bell curve or not, then the final distribution of sample means, if you look at each of these x bars or sample means, that distribution will end up looking like a bell curve. But it turns out that not only do we know that it's a bell curve at the end, we know what the parameters of the bell curve are. So the parameters are the mean and the standard deviation of the bell curve. So it turns out that the mean of this new bell curve will be equal to the original population mean. So the original population mean in this example was 190. So the resulting distribution of sample means will also be the same, which is 190. So the new distribution of sample means will have a mean that is the same as the original mean. So the original mean I'll notate with this symbol for population mean mu. So I'll use this here to indicate the original mean. And the standard deviation of the population I'll use as what we've been talking about before, which is sigma. So the standard deviation of the new distribution of sample means will equal not the original population standard deviation, but the original standard deviation divided by the square root of n. So let's apply it to this example. If the original standard deviation is 10, what is the new standard deviation? So the mean here is going to be the 190, but what's the new standard deviation of this distribution of sample means? So by this formula, it's going to be the original standard deviation, which is the 10, divided by the square root of n, and n is the sample size. So it's each of these samples here that have a sample size of 100. So this standard deviation will be the original standard deviation, which is 10, but divided by the square root of the sample size, which is the square root of 100. Yeah, very good. So the square root of 100 is 10, so 10 divided by 10 is going to be 1. So this new standard deviation is only going to be 1. So why does it make sense that this new standard deviation is smaller than the previous standard deviation? So the previous standard deviation had a value which is 10, which, remember, standard deviation measures the spread of the numbers from each other. So the bigger the standard deviation is, the more spread there is in the numbers. But this standard deviation in the new graph is going to be a smaller number. So why would that make sense? So that means the spread of this new bell curve will be smaller, it will be tighter. So all these values will have less variation or less fluctuation. So the reason for that is if you look at these sample means, we said that they all cluster around the original mean of 190. So all these are going to have very low fluctuation around 190. So that means that's why the standard deviation is lower than the original standard deviation. And in fact, it's a lot lower. This standard deviation is only 1. Okay, any questions? All right, so this is what the central limit theorem is saying, that no matter what the original distribution of individual values is, if you take repeated samples of a certain size, like size 100, and then you take the means of those samples, and then plot the distribution of sample means, then you're going to get a mean value of that distribution being equal to the original mean, but the standard deviation will be less. And the way that you calculate the new standard deviation is the previous standard deviation, 10, but divided by the square root of it. Any questions? Okay, so let's now talk about the assumptions that have to be true. So the whole gist of this is that no matter what the original distribution is, the final distribution will end up looking like a bell curve. The final distribution of sample means. Now, that's true because of our sample size here, and we took the mean of that sample, and every time you take the average, it ended up having this the smoothing out effect, where it smoothed out all this variation, and the sample mean ended up just being clustered tightly around the original mean. And so that's why we ended up with a bell curve here, because we took the sample mean of this sample of a relatively large size. But what happened if our sample size was just 1? Let's say we changed all these sample sizes to 1. And let's say that you take the sample mean of one person. Now, taking the mean of one number doesn't change the number, right? So let's say the sample size is just 1, and then you take the sample mean of that 1, which means it's going to be that random number. Then if you take the distribution of all these random numbers, then what shape do you get? Do you still end up with a bell curve? No, right.
So if you take random point, this minor functions look the same as your original.
Exactly. If you're taking one random point at a time, you might as well be taking random points from your original population, and you're going to get the original distribution. And so this only works then if your sample size is large. Because if your sample size is large, then your sample mean will smooth out all that variation. So the first assumption then is your sample size n needs to be large, and we don't leave it at that. We actually know how large the sample size needs to be. So it turns out that n needs to be at least a size of 30. So the sample size needs to be at least 30. So if each of these samples are 30, then if you take the mean, then you can rely on each of these samples' means to cluster around the mean, and then the final distribution will end up being a bar. So that's if the original sample size is large and at least 30. But let's say that that's not the case. Let's say that we bring it back to a sample size of just 1. If we want this central limit theorem to be true, and the resulting distribution of sample means to still be a bell curve, and our sample size is only 1, what needs to be true of the original distribution to get a resulting bell curve that's still, to get a resulting distribution of sample means that's a bell curve? So in other words, if our sample size is still 1, if this condition is not met, and our sample size is 1, and we find the sample mean for each case for a sample size of only 1, which means we're not doing anything different when we take the sample mean. And then we take the distribution of those sample means. If we want our final distribution to be a bell curve, what needs to be true of our original distribution? Yeah. Yeah, the original distribution has to be a bell curve in the first place if our sample sizes aren't large enough. So the second assumption then is an or, which means any one of these could be true. They both don't have to be true. So or, the original distribution is a bell curve to begin with. Okay, so this is the central limit theorem. This is very abstract right now. I understand if you feel confused. That's totally natural. So in the next class, now that we laid out what this is, in the next class, we'll look at an example which I think will clarify